Hello, we're on the computer this time. One of my colleagues asked me how we choose the mounting system angle when we're designing a solar installation. The simple answer to that is we use what is available from our suppliers, which is a 10-degree pitch mounting. And that's the long and short of the answer. But that glosses over a whole load of more exciting and interesting things, if you're me. And I thought it was worth making a quick video about it. So I have built a beautiful building here. It is a 20 metre by 15 metre, 3 metre high flat roof building in a field in Cambridgeshire. East of England is quite sunny, so that's why I've chosen here. And a building of this size is roughly analogous to a typical UK primary school, and it's a reasonable size of system. The significant thing that this roof doesn't have is a load of air handling units, skylights, and leaks. So it's just a bit easier to design around. We're using 450 watt DAS panels. No particular reason other than we've used them for a few projects recently and they're available. And when I do the inverse calculations later, we're going to be using a 40 kilowatt Huawei inverter, which will be way more than enough for an array of this size because I don't want that to be a limiting factor. The Huawei inverters have a pretty good selection of inputs, so they'll be flexible enough to do what we want here, and it'll keep that as a fixed point. Right then, so like I say, this is currently a 30-ish kilowatt system, but let's go through how we get that on the roof. Onto our roof then, we can go into the Edit Assembly System box. I'm going to remove everything that's there already, so we're starting with a fresh roof. And this is roughly what we put in as a default. So it's a 10-degree pitch. The height from the roof to the bottom edge of the modules is about 0.1 of a metre. And we normally put in a row spacing of about 0.6 of a metre, there or thereabouts. That's just determined by the mounting system that we can purchase. Worth just pointing out, these are the rails that the panels go on. So the panel itself sits up at an angle like this, and there is a foot that sits in up here. And they join together with these tabs here. So they're basically a fixed length. You can get different lengths of these connector sets, but as a rule, you don't really change the spacing of the rows. All right, back on the roof then. If I go into the assembly system, again, we've got the default 10 centimeters off the roof, 10-degree pitch, parallel with the bottom edge down here, and the mounting support clearance of 0.6 meters. Now, because it knows the angle of the panels and the dimensions of the panels, we can actually get it to calculate the mounting support clearance, the optimal clearance, which in this case, it's putting it down as 0.69, no it isn't, 0.769 meters. And so if I click the calculate button, it'll put it in there. But let's just leave it at 0.6 for the time being. So this is what we would normally use. Then I'll do a quick cover area. We've got 70 modules, 31.5 kilowatt peak. And if I do a quick shade frequency calculation, you will see that there is 0.2% shading, and that's just a little bit of shading on the bottom edge of each of these because they are too close together, and the front row doesn't have any shading on at all. Let's just configure that lot. Right, so we're just putting in a 40 kilowatt inverter. There we go. And we'll be at 17, 17, 18, 18. Bum, bum, bum. That will be a complete pain to wire. That will do. Trundle, trundle. And then if we go here, nice quick system to simulate. So we've got an annual yield of 1,113 kilowatt hours per kilowatt peak. And in January, we're at 819. December, we're at 636. And then in June, we're at 5051 kilowatt hours. Remember this. We'll need to refer back to it later. We are now back on the roof, and we're going to edit this just so we are at the optimal row spacing according to the software. And so we're still at 70 modules, 31.5 kilowatt peak. You can see that it's a lot closer to the edges, top and bottom. But if I do the shade calculations, you will now see, ta-da, there's 0.1% shading rather than 0.2. And boom, that's the yield. And we're at 917 in January, 739 in December. All right, now if we go back to the 0.6 that we had before and instead increase that to 15 degree pitch. Now, just for the sake of putting it in there, if it calculates the optimum row spacing again, you can see that's a much, much bigger value there. Because the steeper you tilt them, the more shadow gap it needs. Great. That's not gone well, has it? There we go. All right. So also, because they're now at a steeper angle, we can fit an extra row on, but we're not going to do that. So we're back exactly where we were before. And then we will just configure that again. That one. 17, 17, 18. We'll go through string configurations some other time. Now, all we've done here, compared to the original one, is changed it from a 10 degree to a 15 degree pitch. So that's the change in yield. Then we've got 801 January, 668 December, and we're at 5071 in June. Lots of people think that August is the peak month because that's when we have our summer holidays. June is cooler. So yeah, June is actually generally peak production. More sun, less heat. Now, all I'm going to do here is increase this row spacing a bit to 0.8 meters. And we'll have exactly the same amount of panels on there. Boom, we're still at 70. And this is again 15-degree pitch. And let's just have a quick look to see what that does to the yield. So yeah, change in yield just by increasing the row spacing slightly. And we're at 832, 5076, and 703 there. Like I say, the only thing we've done there is increase the row spacing ever so slightly. This is the one we've just done. So this is the 0.8 meter row spacing, 15-degree pitch. And you'll see if we just calculate the shading, I haven't actually done this yet, I'm assuming we'll still see a little bit. Yeah, so there's still quite a bit of shading there, which is obviously affecting things. So if we now go and let it calculate the optimum row spacing, so there we are. And cover the whole roof. You will see that we've got a much smaller system on there. You may well find it's still got a little bit of shading on there. There you go, 0.2%. So we could actually increase the row spacing a little bit more. But let's just configure this. And we're going to use the same inverter just to keep things consistent. Even though this would be a completely bonkers one to use for this project. Now, I have to say, I was expecting the kilowatt hours per kilowatt peak to go up a lot more than that. Where are we at? So we're now at 875 in January, 713 in December, 4347 in June. So you can see that it's affected the summer yield quite significantly. It's reduced the total kilowatt hours produced in the summer. But actually the winter yield hasn't changed all that much. We've lost sort of 15-20% of summer yield, but you know, winter yield, not at all. And this is the compromise that you're always trying to balance on a system. We're now going to go back to this roof and enter slightly more into the realms of complete fantasy. What happens if we do this at a 30-degree pitch? Now, if we calculate that out, it's going to have an absolutely bonkers row spacing. So we can fit approximately not a lot on that roof. So we're now only at 18 kilowatt peak. We'll come and do a slightly more sensible spacing in a minute. But let's just go through this. We're actually now getting to the stage where we're possibly too low a voltage. Yeah. It'd be interesting to redo this with two strings of 20. Oh well. Alrighty then. So again, you can see the kilowatt hours per kilowatt peak figure has gone up. That's yield per unit installed. But again, overall yield down. January 737, June 2869, December 630. Now, what happens if we keep it at 30-degree pitch, but go to a much tighter row spacing, say 0.8 again? Because at that point, I don't know, what's going to be the maximum row spacing we can get and still get 70 modules on here? Should we go a little bit more? Let's go to 9. Yeah, that's probably going to be about it. I think this won't work. Oh no. Right. How much more wiggle room have we got on there? None, basically. All right, let's configure that up and see what we get. Now, this would be completely impractical to build. It would need half the world's supply of ballast and would probably squash the building in the process. But, you know, we've got a perfect building that doesn't leak, so why not? Maybe it's also built super strong. We've got pretty similar values to earlier. Up here, then we've got 864, 5011, 617. Now, you might well find that this 864 figure, you could improve the January and December yield by removing some panels because you'd get less shading. And that's the compromise. So yeah, remember that, 864. I said I'd show you the shading here. Yeah, see, significant. Right, so 864 is what we're trying to beat. Let's go there. Okay, so we've lost one row. We're not going to really fit much more on than that. We've got much reduced shading from before. And boom, we've still got 864 kilowatt hours produced in January, 739 in December, despite the fact we've now got a smaller system. So we've got less on the roof. We would be able to get away with a smaller inverter. And we've got less of a peak in the summer. All right, I think that'll do for south-facing systems. What happens if we now look east-west? I'm just going to do a very basic sort of standard east-west system here. We're not going to go through all of the different figures. I'm going to do one that was the same size as before with the 70 and one which will be the most we can fit on the roof. All right, so same roof as before. Before, the maximum we could fit on was 70 modules. We're now at 98. So we're in a significantly bigger system. But we don't want that. We actually only want 70 to start with, because that'll be the most comparable. I feel like this must be possible. Hold on a minute. Some finagling is going to have to happen here. There we go. Alrighty, so we're now at 70, exactly as it was before. Let us configure all of that. Boom. Ugh. Now, that would be... actually, that wouldn't be too bad to build. The problem with an east-west system is you get an awful lot more links. All right. Shading-wise, you get quite a lot less on one of these. And you get a better spread throughout the day, morning to evening. But you can see total yield has dropped around about 10%, kilowatt hours per kilowatt peak. June 4836, January 684, December 572. So we've actually dropped off more at the ends of the year than we have in the middle. Of course, the beauty of an east-west system, well, there are lots of beauties of east-west systems. One of them is they use an awful lot less ballast. Another is you can fit a lot more on the roof. A third is you can use inverters rather more efficiently. So whereas before we had 70 modules, we've now got 98. So this is quite a bit of a bigger system on here. Boom. Yes. Determine shading now. Yes. So we're now using the same inverter as we were before, but we've got a much, much bigger system. Kilowatt hours per kilowatt peak, much of a muchness, but total yield across the year has gone up hugely because we've got a bigger system on the roof. 968 in January, best so far. 6767 in June, and 809 in December. So whilst the yield per panel is lower, your yield per inverter is higher, and the panels are dirt cheap. They're about 50 quid each. So the cost of doing a project like this is the people and the scaffolding, not the hardware. So this actually kind of makes sense. Even though you're slightly reducing the yield per panel, you've got more yield per roof. Back to our roof then, what do you do? Do you have a tightly spaced south-facing? Do you have a steeper pitched, looser spaced south-facing? Do you have an east-west? Well, who knows? A lot of it will depend on the roof, because an east-west system might not actually be an east-west system. It might be a northeast-southwest. And the more northerly it becomes, the more of a compromise it becomes. A system like this, the east-west, looks a bit neater, but it's harder to build. It's a lot easier to screw up a system like this, because under each one of these rows, you've got two different strings. You've got the east-facing string and the west-facing string. So there's a lot more opportunity to mess up the installation of this. You've also got many more row-to-row joins to make. A system like this, particularly the steeper the pitch you put them on, the more ballast you need. And the reality is, it becomes increasingly difficult to build. It's difficult to make this look neat. And yeah, it's all about what you can fit on the roof. Reality is, for most of our systems, a south-facing mounting system normally makes the most sense, but it's rarely actually facing south. So you might have a T-shaped building, of which some of it is facing southeast and some of it is facing southwest. And that creates a good spread throughout the day. This east-west is a lot harder to maintain because getting between the rows is that much more difficult. You can just about fit your boot in between this gap here. That's how tight they are. So fault finding on these is a lot more tricky. But at a glance, they look a lot neater because you can't see the cables underneath. And they require fewer mounting system components because they don't have the windshields to attach. And they require less ballast because they're more aerodynamic. So So these systems work on a lot of levels. So long as you've got decent installers that can actually do a decent job of installing them. If somebody messes up installing one of these, it is an absolute nightmare because access is a problem. And it's really, really difficult to test. If you're testing one of these on a lovely sunny day in the morning or in the evening, you can see an obvious difference between the east and the west. You get a massive difference in short circuit current when you're testing them. But if it's a cloudy day or it's near the middle of the day, you'll get fairly similar currents out of the east and the west. So you don't really know whether the strings have been configured correctly, and that can be really really tricky to work out as well. So with inexperienced installers, south-facing, less to mess up, easier to fix. On tall buildings, with experienced teams, where ballasting is a problem, and tall buildings tend to have relatively small roofs for the amount of electricity they use, then your east-west makes sense. Yeah. Swings and roundabouts. Horses for courses. Thanks for watching.